Hey, I'm Sartico1. I try to give you novel arguments regarding abstruse topics. So today I'd like to talk about NMR and more particularly about H NMR or proton NMR. And the reason I want to do H NMR and not carbon NMR is just for the reason that I actually think H NMR gives much more information, useful information than does carbon NMR. And we're going to get into a lot of reasons why that's true. The other thing I want to say is sort of a caveat. If you're looking for a physical description of why NMR is the way it is, this isn't the video. This video is more about a tutorial about how to interpret spectra of sort of like pretty simple organic compounds. So that's what we're focusing on here today. So let's look at a spectrum, and I'm actually going to give you a spectrum today before I give you the compound that it corresponds to, because I want you to start thinking of it in that way. Because ultimately this is how an organic chemist would see it. They'd see this and they'd have to figure out what it is. So I want you to notice a few things. First of all, look at 4.25. There we see a quartet, meaning a series of four peaks that corresponds to the hydrogens off of just one carbon there. In order to have a quartet, what that means is somewhere you have a carbon with hydrogens on it, that's next to another carbon with three hydrogens on it, or that's next to more than one carbon that has a total of three hydrogens next to it. And likewise, that means the singlet that we see at, say, 2.5 will be due to a carbon having any number of hydrogens, but that carbon and those hydrogens must not be next to another carbon having any hydrogens. So now let's look at the molecule that this corresponds to and see if we can start to figure out what's what. All right, so first of all, look at that CH3 with the C next to it at the bottom there. That CH3 with a C is next to no other carbon, is next to no other carbon that has a hydrogen. So that must be the singlet that we saw due to a phenomenon known as spin-spin splitting. What that means is because those hydrogens are not next to any other hydrogens, the local magnetic fields induced by other protons, or the nuclear spin of other protons, will not cause a multiplet of peaks. Rather, there's just one singlet observed. But what about that quartet that we saw at 4.25? What does that correspond to? Well, look at carbon B with the two hydrogens there. Well, you say, oh, that can't be carbon B because it only has two hydrogens. Oh, no, not true. What's important is that carbon A with three hydrogens next to it. And spin-spin splitting, which creates one more peak than the number of hydrogens it's adjacent to, leads to a quartet. And moreover, like we see back on the spectrum, that quartet is at 4.25. Well, if you remember, carbon B from the molecule we are just looking at, that's at 4.25 because it's next to an O and an oxygen, which is electronegative and therefore which will draw electron time away from carbon B, meaning it'll be a bit deshielded, therefore it'll appear a bit upfield. So the only one in the sp3 region that we really haven't considered now is the one at 1.3 or 4, and the reason why that's so far downfield is because that corresponds to the signal from carbon A in the molecule, which is next to another sp3 hybridized carbon. And since carbon isn't particularly electronegative, that signal is not going to be very downfield, or very upfield, I'm sorry. And the last thing I want you to notice is those peaks there at the very, about probably 7.3, those peaks are due to the aromatic hydrogens that we see there. In other words, the ones marked HD and HE. And what I want you to notice about that in particular is in a moment, or maybe next video, I'm not sure, we're going to see an alkene, and that alkene will have hydrogens with peaks at about 5.2 rather than 7.5, and that's due to a phenomenon known as aromatic ring current, which we may or may not get into next video. So anyway, just to recap with this molecule, this one has three sp3 carbons, A, B, and C. A is the one with the triplet, B is the one with the quartet that's upfield due to the O, and C is the one that's a singlet because it's next to no other hydrogens. And the signals from E and D are upfield at about 7.5. So that's what we get from the from the H NMR for this particular molecule. And now we're going to move on to another spectrum. And hopefully our skills will be a little bit honed now that we've considered that stuff. Alright, so looking at this spectrum, we see a couple signals way down there at 7 again. So I guess we're expecting another sort of aromatic ring. And the rest of the signals, it's kind of hard to tell about just how many peaks the one at 2.9 or 2.8 is. And believe it or not, that's actually why I chose this molecule. Because I want to sort of prove the point that you can't really tell how many peaks there are on certain multiplets. You're just going to have to sort of wing it and say, okay, I know there are a lot of hydrogens next to whatever hydrogens those are that are producing that signal. But what I do want to point out is, look how low down that multiplet is. Like, compared to the peak right next to it, I'd say, it's 10 times or so shorter than that peak next to it. Well, the thing with that is, like the shorter it is, the more hydrogens it is that it is next to. And you'll sort of get an idea of how to ballpark that as you go on. So now, look at carbon C there. Carbon C, although it contains only one hydrogen in and of itself, is adjacent to carbons carrying 6 whole Higgs protons. That's quite a few. So I guess what I'm trying to say is, right there we're looking for a multiplet on C, and more particularly on both those carbons with hydrogens marked E, we're going to be looking for a doublet there because they're both adjacent to C. So I guess what I want to do now is just draw a general observation. Anytime you see an isopropyl group like C and E forms, you're going to see a multiplet, more particularly 7 distinct peaks forming one multiplet, and then a doublet. And you will not, like, you see 2 carbons, they're both marked E, right? So you think you're going to see 2 doublets. Wrong. You're only going to see 1 doublet. And the reason why is both those carbons with hydrogens marked E are identical in terms of the nuclear spin properties and the resonance sort of fields that they have. So here we're seeing yet another molecule, and by now I hope we're getting good at this. So look at like 2.4. There we see, I guess, 1, 2, 3, 4 peaks. So that means we're looking for something that's next to 3 hydrogens, maybe something that's next to a terminal CH3 group. And at 1, further downfield, we're looking at, maybe 1, 2, 3 peaks there. Whereas upfield, we see a singlet at 5. So what I'm thinking for that singlet at 5 is, maybe that's next to like an oxygen or an aromatic group or both, and no other hydrogens, because that'll always give you a singlet if you're next to, if you have a carbon bearing hydrogens that's next to no other hydrogens. So that's what I'm thinking for that one at 5, just without looking at the molecule. And then, we have a huge tall peak at 7.4. That's classic sort of aromatic ring action when that aromatic ring has equivalent hydrogens. All right, so here's the actual spectrum. So actually, we're right about the carbon named B. That's the one that's going to give the strong peak at 5. And we know it's that one for sure because A, it's upfield, it's at 5, and B, it's a singlet, and it's next to a carbon in the aromatic ring having no hydrogens and an O having no hydrogens, both of which D-shield it, moving it up to 5. And looking at D and C, those correspond to the triplet and quartet respectively, D being the triplet and C being the quartet. And of course that quartet is a little bit more upfield than the triplet because carbon C is next to a carbonylic group, which will D-shield it because that C in the carbonylic group is very D-shielded due to the very electronegative O's there. So we're going to move on, I think, to one more molecule. Maybe that's it actually already. We'll see. Yeah, I think, okay, that's it for these molecules. I'm Sardico1. Thanks very much for watching. In the next video, we'll get into O and H bonds and actually alkene stuff as well. Thanks for watching.